So we start now the part number 4, in which we make an example of thermoeconomic functional analysis applied to an example of energy system. The example of the energy system is, as usual, the gas turbine system with production of electric power 10, net electric power 10, and recovery of heat in form of production of steam in the heat recovery steam generator number 5. So the water liquid is transformed into steam water. It makes use of only one stream of external fuel, I can say, which is the natural gas flow number C. So we have air compressor 1, air preheater 2, a combustor 3 using natural gas, a gas turbine expander number 4, and a heat recovery steam generator number 5 producing a steam flow number 9. The 7 is the exhaust released by the chimney of the gas turbine to the atmosphere. So now we have to transform this physical diagram, the physical model, into the functional diagram. The functional diagram is in the next slide, and actually it is mostly composed of real components, so compressor, combustor and so on, but also composed of some branching units, some junction units, and some, I can say, virtual units which represent the external, one virtual unit which represents the external environment. So this is actually the functional diagram of the gas turbine that we have seen so far. So there are some, you see, streams connecting the components. Some of them, the continuous line, are exergy flow. Some other, the dotted line, are negentropy flow. So we are both typology. Both can be resource and product, but a typology is exergy flow, another typology is negentropy flow. So let's start with the component 1. The component 1 is the compressor, the air compressor. So normally it receives as a resource, as an exergy resource, you see the exergy flow 1L, which is the mechanical power received from the expander. It is the resource that allows the compressor to operate. It produces as an exergy product a flow B1, which is the exergy associated to its product, which is, remember, its product is the difference between the exergy flow of the exit air, compressed air, minus the exergy flow of the inlet air taken from the environment. So B1 is the product of the compressor. But please notice that the compressor has another resource, which is the resource 1S, which is the negentropy flow resources given to the compressor because it produces entropy. So it has to be compensated in terms of inlet, in terms of negentropy. This flow B1 is given to a junction 7. The junction receives a exergy flow from other components. The components 2 is the air preheater. So the air receives heat from the exhaust and it is preheated. So it has a product, which is the increase of exergy between the inlet air after the compressor and the outlet air after the heat, after the air preheater. So this difference of exergy between the outlet and the inlet is the product of this component. It is the product B2. The product B2 is given to the branching unit 7. So the junction unit 7. Third component, the combustor number 3. It receives as a resource the exergy flow of the natural gas. It produces as a product the exergy flow B3, which is again the difference between the exergy of the exhaust gas of the compressor, not exhaust, the combusted gas after the compressor, and the inlet air before the compressor. So this difference of exergy represents the exergy product of the combustor B3. But remember, notice, also the combustor receive as a resource an edge entropy flow number 3S, which is used to compensate the entropy production inside the combustor. So both, so all the exergy product of the compressor, of the air preheater, and of the combustor, they are all merged in the junction number 7. The junction number 7 produces a global product B4, and this global product B4 is actually the exergy which has been accumulated by the compressor, by the air preheater, and by the combustor into the point, into the stream of highest thermodynamic value in the system, which is the inlet of the gas turbine. So the stream B4 is the point of exergy higher value into the system. It is distributed, this exergy, in the components which are in cascade after this point, which are the gas turbine, the hot part of the air preheater, and finally the heat recovery steam generator. So the B4 is branched into several components. So the B4 is splitted first in a resource 2B, which is given to the expander number 4. The expander number 4 produces the power L1 as a product. Please notice that the expander number 4 also receives a fuel in terms of edge entropy, which is this line. Still, the branching unit distributes exergy to the air preheater, so the hot part of the air preheater, so the exhaust part of the air preheater. Number 2, the air preheater, remember, was producing the product B2, and it makes it by receiving the fuel 1B. Again, the air preheater exchanges an edge entropy, receives an edge entropy because it produces entropy, but also produces an edge entropy because it is also a dissipator of entropy. Third, the last part, no, not the last, the remaining part of the exergy from the branching unit 8 is given to the heat recovery steam generator. The heat recovery steam generator receives exergy, which is basically the difference of exergy between the flow number 6 and the flow number 7, by producing a product which is the steam produced by the heat recovery steam generator. Still, consider that the heat recovery steam generator, because it reduces the entropy of the flow of the exhaust, it is a dissipator of entropy, so it produces an edge entropy. At the end, the very last part of the exergy distributed by the branching unit 8 is given to the last virtual component. So still the flow 7 contains exergy. This flow 7 is given where? Is given to the external environment, mixed from the chimney to the external environment. So you have a closure of the entropy cycle between the flow 7 and the flow 0, which is represented the air, fresh air into the environment, which has to be closed by the role of the environment. So the last remaining part of the exergy, which is the flow exergy of the flow 7 minus the exergy of the flow 0, is the exergy flow 4B. It is given, as you see, to a virtual component 6. This virtual component 6 is the external environment. Okay, this external environment receives the exergy 7 minus the exergy 0, and which is its role? Its role is to close the entropy cycle, like is done in a by a condenser in a Rankine cycle. This role is the production of edge entropy, the flow S1. The edge entropy flow produced by the external environment is after distributed to all the component producing entropy, as we said. So it is distributed to the air compressor, it is distributed to the air preheater, it is distributed to the combustor, it is distributed to the gas turbine, and you receive also this, you see this branching unit, you receive an input also in terms of net entropy from the heat recovery steam generator, because remember, part of the role of the heat recovery steam generator is to dissipate the entropy accumulated into the exhaust gases. So you can consider that now you have a picture of a series of components in which there are, for every component, some resources in form of exergy and in form of net entropy, some product in form of exergy in form of net entropy. All of them have a value in terms of economic value. Solving all the matrix of equation with this functional diagram will give you the value in terms of thermoeconomic cost of every single stream of the system. So in this slide I have only described, reported in writing what I have described already by my talk. So in the functional diagram, the cycle is made of 5 productive units: the air compressor, the air preheater, the combustor, the gas turbine expander, and the heat recovery steam generator. The working fluid can be considered as a collector of exergy. It harvests the functional product in form of exergy increase of the air compressor, the air preheater, cold side, and the combustor. After, the exergy-rich gas flow is distributed the exergy back to the gas turbine, to the heat recovery steam, to the air preheater at the outside, and finally to the heat recovery steam generator. So we have already discussed this. Also, as the entropy content of the working fluid increases inside the plant, in order to allow the cyclic operation of the plant, the accumulated entropy has to be removed in a dissipative component. Therefore, the entropy dissipation is an activity with an economic value. The investment cost of the dissipative component and its operation cost. These are the costs that has to be accounted for. This economic value has to be shared by all the components which contribute to the entropy accumulation, and thus distributed among them. This cost distribution is done using the concept of net entropy flow. In the analyzed plant, during the operation of the air compressor, the air preheater, cold side, the combustor, and the gas turbine expander, there is an increased accumulation of entropy of the working fluid. The accumulated entropy is partially removed in the air preheater at the outside, and especially in the heat recovery steam generator, but not completely. Therefore, in the functional diagram, also a not productive component has to be introduced, which is the dissipative unit 6. It has the role of removing the residual entropy in the working fluid in order to close the cycle. This dissipative component simulates the role of the external environment, so it is the environment. In this slide, I only report for every single component the resources in terms of exergy or net entropy and the product in form of exergy and net entropy. So here I list the air compressor, the air preheater, and the combustor. You can read. I've already described it, but you can read it again. And in this slide, I report the gas turbine, expander, the heat recovery steam generator, and the dissipative unit, which is the role of the condenser. So for every one, there is the resource flow in form of exergy in form of net entropy, and the product in form of exergy and, if exists, in form of net entropy. Also, there are some, as I said, branching unit, as the branching unit 9, collecting the net entropy from the dissipative unit 6, and the branching unit 8, collecting the exergy from the compressor, the air preheater, and the combustor, and the branching unit 10, which split the power produced by the gas turbine into net power and power to the compressor. Also, there are the union unit 7, the junction unit 7, that express the collection of exergy flow from compressor, air preheater, and combustor. With this, I completed this part number 4, which is the description of the functional diagram of the example of the gas turbine. Now we will move to the writing of the matrix equation in the way that we have described in the previous part for this functional diagram, and to solve it in terms of calculation of the unit thermoeconomic cost.